Okay, and if you have any questions about that, send me an email. So today we are going through gravitational fields. So what causes gravity? Think about that. Well, masses cause gravity. But why do masses cause gravity? What's going on there that causes them to create gravity? Is there like gravitron particles or something like that? So that's what we're going to talk about today. So to understand how gravity works, you need to know the difference between forces and fields. So a force is a push or a pull. A field is a 3D area of influence around an object that creates it, and the thing that creates it we call the source. So not everything is affected by certain fields. So the thing that's affected by fields we call the test object. So we can stick a test object in a field, see if it's affected by it, and that's how we can detect the field. So we discussed different fields in physics. We discussed gravitational fields in physics 20, and then in physics 30 we discuss electric and magnetic fields. So to get you an idea of the difference between forces and fields, I have a little analogy here. So here is some oiled up buff dudes. Okay, so, oops. Sorry, let's get those oiled up buff dudes back on the screen there. So we have two objects here. This is one person. So this person, let's get some eyeballs in there, likes the oiled up buff dudes. He likes their body, their six packs, their oil. Look at his piercing eyes here. This guy likes everything about these oiled up buff guys. So let's draw a little body on him too. There we go. So as this person is walking through this field created by this oiled up buff guys, he sees the oiled up buff guys and immediately experiences a force, right? So this guy over here will be like, ooh, oiled up buff guys, very nice. And he'll want to touch his abdominal muscles and be like, yes, I like this a lot. So the oiled up buff guys created this field, and this guy who likes the oiled up buff guys, likes the ab muscles, experienced a force because of it. Okay, so let's talk about another situation. So this is situation number 2. So this guy does not like oiled up buff guys. Okay, so as this person walks through this oiled up buff guy field, right, because there's this field of oiled up buff guys in here, this person doesn't experience a force, they go right through, right? So no matter what, the oiled up buff guy field exists, but you have to have the right test object, the right person to go through to experience a force. So fields always exist, right? There's a gravitational field, there's a magnetic field, right? Compasses work, but you need the right object, right? We can't sense a magnetic field because we're not the right test object, but you stick a compass and it'll line up with Earth's magnetic field. So the field exists, it's an area of influence and can exert a force if the right thing walks through it. Okay, so we'll talk about gravitational fields. So what causes a gravitational field? Well, a mass. Okay, so a mass causes a gravitational field. What is affected by gravitational fields? Well, anything with mass, right? Let's put another mass. So if I stick an object with mass near this, say this is Earth, what that object is going to do is it's going to start to fall towards Earth. It's going to go towards the center of the mass. So gravitational field lines can be drawn and show the direction and the strength. So to draw in the direction of a gravitational field, we just place an object here. Which direction would it go? Well, it would go towards Earth. It would go towards Earth. Right? It would go towards Earth. It would go towards Earth. Gravitational fields are always going towards the center of the mass of the object. And then to figure out the strength, what we look at is we look at the density of the lines. So what that means is if I extend, actually let's draw one more line in here. And I extend these lines out like this. Here these lines are closer, so they're more dense. So this means that the field is stronger, right? If out here the lines are less dense, so that means that the field is weaker. So if we wanted to draw a really strong field, we would draw really, really dense lines in there. That's what we would want, right? And as we get further away, those lines get further apart. So to find out this formula for a gravitational field, we can combine these two formulas that we know, right? This equals Fg, this equals Fg. If they both equal Fg, then, well, mg is equal to g m1 m2 all over r squared. Right? We can just combine them together. So one of these masses is going to cancel out. But you have to think of which one. So to think of which one cancels out, you think of here is the Earth, and here is a person standing on the surface of the Earth. So if I'm using this formula here, do I want the mass of the Earth or the mass of the person? Well, this is the mass of the person. Right? And if I was trying to find the force of gravity between these, mass 1 would be the person, and mass 2 would be the Earth. Right? So the one that cancels out is the person, right? The person cancels out. So this mass that's left here is the Earth for most situations, or we can say the source. It's the source of the gravitational field that's left over. So this is the formula that we end up getting, where G is our gravitational field strength, and it can be in meters per second squared or newtons per kilogram. G is our gravitational constant, mass, m is the mass of the source, and r is the distance away from the source. Okay. So you can find this formula under forces and fields on your data book. There's a term that's going to come up quite a bit, which is the term altitude, and you need to know how altitude differs from r. So altitude refers to the distance above the Earth's surface. R in the formula represents the distance from the center of the planet. Okay, so if we have here, so if this is Earth again, right, this is the surface of the Earth, this would be our altitude right here, and this would be R right here. So if this is Earth, if we wanted to get between our altitude and our R, well, we would have to know this distance right here, and this is our radius of Earth. And we actually know our radius of Earth. So to find our radius of Earth, we can just look on our data book, right? This is all the other planets. Earth is over here, so radius of Earth is right here, which is 6.37 times 10 to the 6. So 6.37 times 10 to the 6 meters. So if I add 6.37 times 10 to the 6 onto my altitude, then I'll get radius. And if I have my radius and I want to find altitude, I would subtract that 6.37 times 10 to the 6. So let's do an example. Calculate the G field at a point in space that's twice the radius of Earth away from the center. So we're going to use our new formula. So we know that our G field on the surface of the Earth is 9.81. No matter where we are, it's 9.81. And as we get further away, what happens is it's going to get weaker. So we want to find out how much weaker that is, right? And I can show you that it's 9.81. If I just plug in, if I just go G times the mass of Earth, 5.97, times 10 to the 24, divided by the radius of Earth, 6.37 times 10 to the 6 squared, then I end up getting 9.81, right? That's the gravitational field here on Earth, and that's what makes things accelerate towards the ground. So if I want to figure out twice the radius away, well, you don't have to do some crazy calculations for that. It's just going to be twice the radius, so twice squared. We're not making any changes on top. On the bottom, it's changing by 4. So it's going to have a fourth of the gravitational field. So if we go back to our calculator and we divide that by 4, well, if we're twice the radius away from Earth, that's what our gravitational field's going to be, 2.45. Okay, and that's it. To determine a point away from Earth where Earth's gravitational field strength would be 1/3 the field on the surface. So same sort of question. So pause the video, see if you can do it yourself, and I will go through it. So to start this question, if you're having trouble getting started, we're trying to determine a point away from the Earth. So we're trying to find how far away we are. So we're trying to find R. So whether I give you numbers or I don't give you numbers, you still need to isolate for R. So I'm going to move R squared up top, I'm going to move G down below, and I'm going to square root it. So I end up getting R is equal to square root of GM over G. So the only thing that I'm changing is I'm making gravity 1/3, but the acceleration due to gravity or gravitational field is square rooted, so I have to square root this as well, right? So I'm not making any changes on top. Square root 1 is 1, and then square root 3 is square root 3. So instead of saying 1 over square root 3, I can just say square root 3. So my radius is going to be square root 3 times bigger is what it's going to be. So all I would have to do to actually find that radius is I would take the radius of the Earth and I would multiply it by square root 3. And that's how far away I would have to be to do that. So let's do another board question. What is the gravitational field on the moon's equator? So remember that you have this information here that you need to use. Let me go over to my board. Actually, no, I don't need to go over to my board for this one. Okay, so try it out. Okay, so what we need is we need G. And then we need the mass of the moon. So the mass of the moon is right there, 7.35 times 10 to the 22. Divided by the radius. So we don't want the orbital radius because we just want to know how thick the moon is. That's how we find it. So we just need the radius of the moon, which is 1.74 times 10 to the 6 squared, and then we get that, right? And we said that the moon has 1/6 Earth's gravity, right? And it's about 1/6 Earth's gravity. 1.62 is what we'd find. Okay, so 1.62 is our answer. Okay, and this last one is quite a tricky one. We're going to do this one together. So we have two 10-kilogram masses. We'll call this mass 1, mass 2. And we want to determine the gravitational field at point P, right? So just like with the oiled up buff guys, there doesn't need to be anything there to have a gravitational field. So here at point P, there's a field that exists from both of these, but we want to know what it is. So first thing that we would do is if we just had mass 1 would create an attractive gravitational field, right? It would always go towards mass 2. And if just mass 2 were there, well, we would have a gravitational attraction to mass 2. So this is what it would look like. So what I need is I need to know the distance between these, because I don't have that. And I know this is 5, this is 15, so I can find the distance between it by just using Pythagoras. So that's the first thing I'm going to do. Let's clear this. So I'm going to go 15 squared plus 5 squared, and I'll square root that. And I get 15.881. So this is 15.881 centimeters and 15.881 centimeters. And I'll try to use that full answer there. And I also need this angle here. I'm going to need this angle here so I can go tan because I have opposite and adjacent. So if I go tan -1, of opposite over adjacent, so 15 over 5, I end up getting 71.565. and this is 71.565 degrees. Okay, so I need those to start to do the question. Okay, so let's switch over to this screen here. Let me just draw on what we did there. So we have point P, and we have object 1, object 2. So we said that this was 71.565, and this is 71.565, and then we were 15.881 centimeters away. Okay, sorry, I know that's underneath my calculator, but I just wanted to have that there. And of course I drew it too high, so it's off the screen. I can fix that. There we go. Didn't use my little legend for the top there. That's okay. Okay, so first thing we can do is we can find the gravitational field just from one. Just imagine that this didn't exist and we just had a gravitational field from one. Well, that's really easy. Okay, so it's just going to be 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. And then mass 1 is 10 kilograms. And then the distance between them, we need it to be in meters. And I'll use that full answer squared like that. Okay, so I'll plug that into my calculator. 6.67 times 10 to the negative 11 times 10. I'll put brackets around it. Oh, I didn't mean to clear all that. Shoot, I wanted those numbers. Sorry, I'm going to Pythagoras 15 squared times 5 squared. Oh, 15 squared. Sorry, 15 squared plus 5 squared. I don't know how to do Pythagoras anymore. Sorry, I just want that full number there. There we go. Okay, now I'm ready. So I'm going to go G times 10 divided by my answer, divided by 100 squared. Oh man. Sorry, I think I'm going to take that answer and divide it by 100 here. There we go. Now it's in meters. And now I'm really ready to go. There we go. So that's our gravitational field from G1, which is 2.668 times 10 to the negative 8 newtons per kilogram or meters per second squared. We can give them both. And this one's the same mass, the same distance away. So that's actually what G1 and G2 are. They're the same thing. They're going to be 2.668 times 10 to the negative 8 newtons per kilogram. Okay, so what we're doing is kind of like a free body diagram, but only for fields. So when we have these two fields going that way, right, we have two vectors going that way like that. We can do a tip to tail like that, or what we can do is we can do an RCS chart, right? Because then they're not going to make a right angle triangle, or maybe actually they probably will, but I'm just going to do an RCS chart to remind us of how to do an RCS chart. So this is X, this is Y, this is vector 1, vector 2. So both of them have the same magnitude, but what we need is we need a direction in RCS. So remember that is 0, 90, 180, 270 in RCS. So this one is 71.56, and this is 71.56. So that means that this angle for number 1 is going to be 270 minus that 71.565. So if I go 270 minus 71.565, then we end up getting 198.435. Because remember, we need the angle in RCS, so that's what I'm doing here. So 198.435. And then this one is going to be 270, which is down, plus another 71.565. So it's going to be 341.565. Okay, so I have my magnitude and I have my angle. So then what I can do is I just go 2.668 times 10 to the negative 8. X is cos, y is sine. So I just go cos 198.435. And this is 2.668 times 10 to the negative 8. Cos 341.565. And I would do the same thing for sine. And then 2.668 times 10 to the negative 8, sine of 341.565, like that. Okay, sorry, that's kind of messy, but I'll put in my calculator here so you can see a little bit better. Okay, so let's do this. So 2.668 times 10 to the negative 8 is my magnitude, and then I'm going to go cos of my angle, which is 198.435, close my bracket, and I need to add it to 2.668 times 10 to the negative 8. And I'm going to go cos of my angle, which is 341.565. Close my bracket. Right, and I end up getting 0. And that makes sense because this has an x component, it's an equal angle. That's the x component. So those two x components are going in opposite directions and they're going to cancel out. So let's find our y. So to find our y, all I have to do is type in the exact same thing, but switch my coses to sines. And we get that it's going downwards, which makes sense. And it's going downwards at 1.68 times 10 to the negative 8 newtons per kilogram. 1.68 times 10 to the negative 8 newtons per kilogram is what we end up getting as our answer. Actually, it would be 1.69. There we go, and that's it. Okay, so there's some 2D questions in the homework. If you have any trouble, send me an email and I can help you out, but that's how you would do it. Okay, find the magnitude, throw it in an RCS chart if it doesn't look like an obvious right angle triangle. Okay, this is your homework questions. Those standard of excellence are those 2D ones. So give them a go, see if you can do it. There's definitely going to be a 2D on your quiz, so try that out. Okay. If you have any questions, let me know.